So this week is special because it's we have one of our very own. So it's my pleasure to host Semeon Artamonov. Sorry if I mispronounced your name. It's maybe please say it correctly.
It's absolutely correct. Yeah.
Okay.
Thank you.
So Semeon is a postdoctoral fellow in the math physics lab at the CRM. And prior to that, he was actually a Moray visiting assistant professor at the University of California, Berkeley. And before that, he did his PhD at Rutgers. And the topic was generalized quasi-Poisson structures and non-commutative integrable systems under RedTech. And prior to that, he did his undergraduate studies in Moscow, and I don't know if there's a master's in there. Yes, there's a master's in applied mathematics and physics. And today, it's a work that he'll present that he has done with Marco and Jacques, right? And it's about the CKP hierarchy and Lagrangian Grassmannians. So
Marco is John.
John and Jacques.
John and
J.Hurtubise and J.Harnad.
Oh yeah, John. Sorry, so not Marco. I'm sorry.
Yeah.
Sorry, John. Sorry, Marco.
Thank you very much, William, for the introduction and for the invitation to give a talk at the seminar. So I will talk about our work, which has just appeared on the arXiv, plus maybe some things which were not included in that text due to the size constraints. And it deals essentially the relation between the infinite dimensional Lagrangian Grassmannians and the KP hierarchy of type C. Okay, so while preparing this talk, I thought it will be completely inappropriate if I would give a talk on the hierarchy of differential equations without writing a single PDE on the blackboard. So here it is. As a warm-up, let's say a few words about the history. And seriously, I wanted to kind of emphasize that although my talk is really algebraic, and I will be talking about the Plucker relations, the infinite dimensional Fock space, etc., that all these problems are deeply rooted in something very concrete, and namely the equations of shallow waves, and actually approximation of the equation of shallow waves in 2D. And that's essentially where the idea of the KP hierarchy came from. Okay, so probably the first appearance of similar equation dates back even to 19th century, when Cortex de Vries observed solutions, of waves, stationary waves in the channel, and this is the nonlinear equation which describes shallow waves in one dimensions. So, and kind of it has a two-dimensional generalization. So, and this is not exactly the equation which would describe the shallow waves. It's rather certain asymptotic behavior. You can see that x and y do not enter on equal footing here. So it's like a wave which is moving primarily along the x direction, slowly changing with respect to y. So this is a nonlinear equation. There is no immediate way to solve it in 2D. However, how it often happens in mathematics, you can, instead of solving a narrow problem, you can consider a much bigger problem, and it would turn out to be easier to solve. So instead of solving one PDE in 3 variables, let's actually solve an infinite collection of PDE on infinitely many functions in infinitely many variables. So basically, instead of having x and y, x, y, and t, let's just have an infinite series of variables t1, t2, t3, t4, t5, and infinitely many functions of those variables. Now let's introduce the so-called KP hierarchy. So it has a number of different equivalent definitions, but for my purpose, it would be convenient to use the lax operator approach. So let's look at the pseudo differential operators in this variable t1. So for now, this d by dt1 and d by dt1 to the power minus j are just formal symbols with an obvious commutation relation with with the variables, which originate from the Leibniz rule and the integration by parts. So let's look at the following formal operator with just general coefficients uj, which are functions of this infinitely many times. If we look at the kth power of this lax operator, then it will start, from the derivative from the d to the power k and subleading terms. And out of those subleading terms, we can select only the non-negative derivatives, and let's call it lk plus. So that will be an operator to which we would refer as dk. So we can consider the following system of partial differential equations. Well, actually, one has to verify that this equation star defines a system of PDE, but it does. So if you commute this LK plus with L, you get a formal pseudo differential operator, right? At the same time, if you just derivate the coefficients with respect to the TK, you also get a formal pseudo differential operator. So let's just move all the d's to the right and equate the left hand side to the right hand side. What you would get is an infinite system of PDE on this uj of t. So this is the so-called KP flow equation. And the KP hierarchy is defined as the compatibility condition for this KP flow equation. So basically, we look at the operators dj, and we take the zero curvature equation for this operator dj. And again, if you expand everything out and collect coefficients in front of the pseudo differential operators, you will get a system of PDEs on this functions uj of infinitely many times. And that's the so-called KP hierarchy. So also this equation is known as the Harav-Shabbat equation in this context. Okay, so these are the basic references when this theory of KP hierarchy has appeared. Let's try to solve the equation star. So the good thing about this lax operator, which starts from dt1 and contains infinitely many negative formal operators dt1 to the minus j, is that one can bring it to the form dt1 by conjugating with certain operator w. So, and the way you determine this w is you start with a general operator with coefficients wj of t, and if you conjugate, then you can solve a triangular system of equations for this wj. So there is always a way for any pseudo differential operator of this form to present it as w dt1 w inverse for this operator w. Okay, so this allows us to make a change of variables in the KP flow equation. So let's see what the KP flow equation means in terms of the pseudo differential operator w. And here's a nice theorem, which is known as Hirota bilinear relation, that the operator w, this pseudo differential operator with coefficients wj, which are functions of infinitely many times, gives rise to a KP solution if and only if the so-called Baker functions psi of z of t satisfies the Hirota bilinear relation. So this psi of z of t is nothing as just application of this operator to the following eigenvalue of dt1. So if we look at the function, which is the sum of ti zi for z to the I for some parameter z, and apply w, what we will get is essentially this expression in the blue. That will be 1 plus sum wj z to the minus j multiplied by the original function, and it's called the Baker function. Knowing the Baker function is essentially the same as knowing all this infinite sequence of functions wj, right? So knowing the Baker function is the same as knowing the operator w, and the condition on operator w to define a KP solution is written as a residue of these Baker functions. As a condition that the residue of this Baker function at z equals 0 vanishes identically as a function of two collections of infinite set of variables t and s. Okay, so we had an infinite system of PDEs in infinitely many variables, which we reduced to an infinite system of quadratic equation of algebraic equations in infinitely many variables. And that's, as you might guess, infinitely many times better. So how do we solve now this system of algebraic equations? And the way to solve, to get the solutions to the system is through the so-called Sato formula and the Sato theorem, which basically tells us that psi of z and t is a Baker function of the KP hierarchy, if and only if we can find another function, tau of t, which is known as the tau function of the KP hierarchy, such that this psi of z of t is actually the fraction of tau evaluated at a shifted point over tau multiplied over this original sum of ti to the zi. And this angle bracket z minus 1 is the following infinite vector, which start with z inverse, then one half z to the minus 2, 1/3 z to the minus 3, etc. So now kind of the main beautiful part of that talk. So that, okay, so let's make this change of variables. Let's plug this expression for the Baker function into the Hirota bilinear relations. And the theorem by Sato tells us that there is actually a geometric description of when this tau of t, when this tau of t gives rise to a Baker function of the KP hierarchy. So, and it says that an element tau of t in the formal power series, in the ring, which is formal power series in these variables t1, t2, etc., is a tau function of the KP hierarchy, if and only if coefficients of expansion of this formal power series in the Schur functions basis. So these are the Schur functions, and the Schur functions give a basis here. So kind of this tau of t is a tau function of the KP hierarchy, even only if the collection of these coefficients pi lambda satisfy Plucker relations of an infinite dimensional Grassmannian, which I'm about to define. Oh, and I forgot to mention it in the very beginning. Of course, I encourage questions at any moment of my talk. So if you want, please feel free to unmute yourself and ask questions. Okay, so let me move on, and let me kind of introduce the main object of my talk today. Well, one of the two main objects of my talk today, and that's the KP hierarchy of type C. So we have kind of the original KP equation, and now we say that this L is a Lax operator for the CKP hierarchy. Well, if it satisfies the original KP flow condition, which was written in the second slide, but also if it is anti-self-adjoint, meaning that if we take the LCKP and take conjugate inverse, then it will be the minus LCKP. So now kind of it ranges, well, the solutions to the usual KP hierarchy, which is also a KP hierarchy for the GL infinity or type A KP hierarchy, are related to the usual Grassmannian. So it's kind of natural to expect that the solutions to the KP hierarchy would be related to Lagrangian Grassmannian. And that's kind of precisely what I will be showing today throughout my talk. Somehow it was not part of the original Sato theorem. So kind of that's the gap we will be closing today. Okay, so and by the way, any questions so far before I move into formulas? Okay, so let me start by defining the finite dimensional Grassmannian, first the usual Grassmannian, and then I will impose Lagrangian condition. And because for my talk, I will be interested in Lagrangian Grassmannians, when I will be talking about usual Grassmannians, I will only be interested in Grassmannians of n-dimensional space in 2n-dimensional space. So let's start with some vector space with a basis labeled by negative integer from -1 through -n. And let's consider its dual and take the direct sum of the vector space with its dual and denote this as Hn. So we can introduce, we choose the basis on the dual in the following way, that EI applied to E minus J is this delta function with some sign. So the reason for the signs and for the ugly labeling here is to make it consistent with the infinite dimensional case, which is described by the Siegel-Wilson Grassmannian. So by construction, this Hn is naturally isomorphic to its dual, and we can actually, for all I from -n to n-1, we can say that EI dual is just an element of Hn with this sign. Okay, so now we can look at the exterior algebra on this finite dimensional space, and we can look at the n forms in this exterior algebra. So this n forms, they're given by elements EI1, well, the basis is given by elements EI1 through EIN, where this I1 through IN are distinct integers between -n and n-1. And on the space of, and on the exterior algebra, we have the action of the so-called Clifford algebra. So we can look at the operator, which take the wedge product with EI, so that will be psi I, and we can take the interior product with EI star, that will be psi I dagger, and they will satisfy the following anti-commutation relations. So of course, kind of the wedging with different EI anti-commute, so is the psi dagger operators. However, kind of if we anti-commute psi I with psi j dagger, we get the delta function. Okay, so now the Grassmannian of V in Hn is essentially the space of all embeddings of V into Hn. So we can use the Plucker map to introduce the coordinates on this Grassmannian. So let's say that we have a subspace W small of V, and let's choose a basis on the subspace W1 all the way to Wn, and let's just wedge all the elements of this basis. So this will give us an element of the exterior algebra of of degree n in exterior algebra on Hn, and kind of the coefficient in front of the form EI1 all the way through EIN is the so-called Plucker coordinate. Of course, Plucker coordinates in general are not independent. There are relations between them called the Plucker relations. And the best way to see this in the coordinate ring description. So let's say that we consider the we consider the homogeneous coordinates, which essentially describe n tuples of vectors in 2n-dimensional space, right? And we look at the homomorphism from the coordinate ring of this. Well, I mean, from this, it's essentially polynomials in the Plucker coordinates to this polynomials in homogeneous coordinates. Well, this map will have a kernel given by Plucker relations, And the quotient by this kernel is precisely the coordinate ring of Grassmannian. So this way we can describe Grassmannian as a projective algebraic variety. Now, kind of if we look at the particular homogeneous coordinates, then we can introduce big cell by the following condition. So let's say that out of this n by 2 n matrix of homogeneous coordinates, the first half is invertible. So when the first half is invertible, we can bring it to the identity form, and the remaining n by n matrix will be essentially the affine coordinates on the big cell. And the big cell is determined by the condition that the first matrix is invertible. So what does the symplectic, what does the Lagrangian condition means here? So let's say that we are now looking at 2n-dimensional space with the following symplectic form. So we take E minus I, wedge E I minus 1 dual, and remember that we have kind of identified by construction HN with HN dual to simplify the notation. So this expression is going to be really thought as an element of the as a wedge product of EIs. So we will not use the stars anywhere. Okay, so now kind of the wedging with the symplectic form defines an operator on the exterior algebra, this omega n, and there should be hat, which essentially takes the form of degree k and send it to the form of degree k minus k plus 2, and the same with the daggers. So kind of this omega n hat and omega n hat dagger, they give us the presentation of the Heisenberg algebra, and the exterior algebra on HN as a module of symplectic Lie algebra decomposes into irreducible submodules, where these irreducible submodules are essentially kernels of omega n hat on the corresponding homogeneous component, and then raised by an appropriate power of omega nj. Okay, so now to define the Lagrangian Grassmannian, we want to look at the isotropic embeddings of the space V into the space HN, So let's give a definition of Lagrangian Grassmannian as the preimage of the Plucker map of the module P and N. And this thing P and N is essentially the kernel of the operator which wedges with the symplectic form on the nth dimensional on the homogeneous component of degree n of the exterior algebra. So now on the level of the coordinate rings, this will imply that kind of instead of mapping everything to the coordinate ring, to the polynomials in homogeneous coordinate, we map it to the polynomials in homogeneous coordinate quotient by the Lagrangian isotropic condition. Quotient by the fact that if we, and there's a typo, of course, that meant to be wedge, that meant to be omega of Wi, Wj. Oh, Wj, Wk. So we quotient by that, and what it gives us that the kernel now of this homomorphism will be will contain the usual Plucker relations. And the linear relations, which tell us that the value of this phi L on all submodules except P and N are 0. So the coordinate ring of Lagrangian Grassmannian consists has the same collection of generators, the Plucker coordinates, but the relations now are the quadratic, the usual quadratic Plucker relations and linear relations, which describe the Lagrangian isotropic condition. Okay, so now let's kind of do the same in the infinite dimensional setting. So let's look at the infinite dimensional vector space with bases labeled by integers. So now EI will be labeled by integers, and we can think of it, as the basis on, polynomial, for example, functions, but of course one can consider completions of that, etc., which are essentially z to the minus I minus 1. And then we can define the symplectic form as the following integral over the closed contour of f of z g of minus z. So if you basically expand f of z and g of z in the powers of z and look what this omega means, then you would get precisely the formula I used in the finite dimensional case. Well, that was, of course, the reason I used omega n with these factors on EI and EJ. Okay, so inside this space H, there are, well, it decomposes it as a direct sum of two isotropic subspaces. That's H plus, which is spanned by the negative E, and H minus, which is spanned by non-negative I. Yeah, notations are great, but unfortunately, that's the standard terminology here. And instead of the exterior algebra, we will have a Fock space. So informally, one can think of elements of the Fock space as this infinite wedge products, where Li is decreasing sequence of integers, which essentially saturates. This means that after certain, so if you start with E, I don't know, E5, wedge E3, wedge E minus 1, wedge E minus 4, then after some moment, it saturates, meaning that all consecutive negative integers are included. So, so this is the Fock space. And on this Fock space, you can define the action of the Clifford algebra by exactly the same formulas as were before. So kind of psi I corresponds to this wedging with EI, where essentially if we wedge with something, we'll move it we move it to the right until kind of everything gets in order. Well, and if this element EI already appeared in the sequence, then the action of psi I is 0, and same with psi I dagger. And we can define the operators omega hat and omega hat dagger, which contain infinite sum. However, this infinite sum on saturated sequences, only finitely many of these terms will act by non-zero. So the action of this omega hat and omega hat dagger on this Fock space F is well defined. Okay, and now similarly to the finite dimensional case, we have decomposition of the Fock space into irreducibles. So the irreducibles are again kernels of the omega hat dagger operator on homogeneous component n minus 2j, raised by the omega hat to the power j. So one can do an exercise and prove that those are irreducible. Well, it's fairly easy to see why they are decomposable, but because we're in infinite dimensional case, some extra work requires to show that they are actually irreducible, but that's true. So, and now we can define the infinite dimensional Lagrangian Grassmannian as the pre-image with respect to the Plucker map of this F00. So this F00 is the kernel of the omega. So F00, if we unravel the definition we had before, is essentially the kernel of the operator omega hat restricted to the homogeneous component of degree 0. Kind of homogeneous component of degree 0, I forgot to say it, if you look at this sequence, right? So with every sequence which saturates, you can essentially look at how many elements are there before it saturates. And for example, in this case, you will add to -4, you will add 3, and this will be element of homogeneous degree -1, which is also known as fermionic charge in this case. Okay, so we have this Lagrangian, infinite dimensional Lagrangian Grassmannian, which is a subvariety of infinite Grassmannian of H plus and H, and it describes isotropic embeddings of H plus into H. So essentially, it describes all the injective maps from H plus to H such that the image is an isotropic subspace with respect to the symplectic form. Okay, and now let me move to the main statement. Is that if we take an element of the infinite dimensional Lagrangian Grassmannian and consider its Plucker coordinates, which are labeled in this case by Young diagrams, satisfying all the Plucker relations of its coordinate ring, then the linear combination of Schur functions, which in principle can be, we can take infinitely many non-zero Plucker coordinates, because the Schur functions, they have homogeneity of exactly of the number of boxes in lambda. You can add infinitely many elements like that and still get a well-defined element of the formal power series. Then kind of if you take the Plucker coordinates corresponding to an element of an infinite dimensional Lagrangian Grassmannian and take the corresponding linear combination of the Schur functions, you'll get a tau function of the CKP hierarchy. Also kind of another part is that this CKP tau function will satisfy the following condition, that if you negate the even times, it will be equal to itself. In particular, it would mean that if you take the derivative of this tau function with respect to even times and set even times to 0, right, then you would always get 0. And this kind of this result is an interesting connection with an earlier result by Khrushchev and Zabrodin, which have provided necessary and sufficient condition for the tau of t to provide solution of the CKP hierarchy. And namely that they said that these derivatives are enough to guarantee that this is actually a solution to the CKP hierarchy. Okay. So this is kind of this is the primary result I wanted to present. And let me stop for questions and then say a few words about the applications. Any questions so far? Let me say a few words on something which is not in the paper referenced on the first slide of this talk. So let me say something about the evaluations of the tau function. Okay, so let's say that we take an element of the infinite Lagrangian Grassmannian, the usual infinite Lagrangian Grassmannian, and look at the following sequence of the evaluations of the tau function. Let's call applications to discrete integrable systems. So let W be an element of the Grassmannian, and tau sub W of t be the corresponding KP tau function. KP tau function. Question. Okay, so let's look at the let A be a free abelian group generated by infinitely many generators, alpha I, also known as an infinite dimensional lattice. An infinite dimensional lattice. No. Lattice. And let's define the following evaluations of the tau function. So let's say that Hn W of t is the product of I less than j, xi minus xj to the power ni and j, this tau function evaluated at the following point, t plus sum from I equals to minus infinity to plus infinity of ni xi. So here xi are just generic parameters. Xi are generic parameters. Okay, so proposition 1.
Semeon,
Yes?
I don't think you described what the square bracket means.
I actually gave a definition for the square bracket of Z inverse, but let me repeat that. So in this case, that's xi squared over 2, xi cube over 3. So that's this infinite vector, and we add it to the vector t1, t2, etc. So that we shift the argument in the following way: that the first argument we shift by xi, the second argument we shift by xi squared over 2, etc. And we can do that with integers, with the integer coefficients described by elements of an infinite dimensional lattice. So now proposition, and that's essentially a corollary of what we did in the paper. That if we look at this for any base point and 0 in our infinite dimensional lattice, we have a homomorphism of the coordinate rings. We have the homomorphism. Oh, I should probably move to the next slide. Following is a ring homomorphism. So let's say phi w and 0, phi w and 0, and let's see what's the. It's essentially from the coordinate ring of the Grassmannian of h plus in h to the formal power series in t, variables t, which takes the Plucker coordinate lambda and sends it to essentially the evaluation of n0 plus some alpha I ni, alpha I and I. Oh, sorry. Alpha I ai, I equals 1 through r minus some alpha minus I minus 1 beta I equals 0 to r w. So here ai and bi are Frobenius indices of partition lambda. I will not kind of go into technical details, but the upshot of that is evaluations of the tau function define an entire lattice of points, an entire entire lattice of points in the infinite dimensional Grassmannian, and H plus H. And the same is true. Same is true for CK, well, square of the CKP tau function, square of CKP tau function, and Lagrangian Grassmannian. So if we take the square of the CKP tau function and evaluate it at a different points on a lattice, then its evaluation would correspond to the Plucker coordinates of an infinite dimensional Grassmannian. And if we shift the base point, we get a new point in the infinite dimensional Lagrangian Grassmannian, and they would glue nicely. So that allows to solve a lot of integrable, discrete integrable systems using evaluations of the tau function. And that in particular includes the the so-called hexahedron recurrence introduced by Kenyon and Pemantle in 2014 and 2016, and also the hyperdeterminantal recurrence introduced by Kashaev, which is a reduction of that. So let me stop here, and I will be happy to answer the questions.
Thank you, Semeon, for a very nice talk. Applaud Semeon, and the talk is now open to questions.
I think I'd like not to ask a question because I'm a collaborator on this, but I'd like to just add some clarifying remarks, which might make it a little easier for the rest of the audience to understand what Semeon just said. This proposition, what it means in English is that the Plucker coordinates on the Grassmannian, which satisfy these Plucker relations, quadratic Plucker relations. And those Plucker relations, I don't know if Semeon made it very clear, but those Plucker relations are completely equivalent to the Hirota bilinear relations of the KP hierarchy. So they are another way to say that something is a tau function. If you expand it in the basis of Schur functions with coefficients pi lambda, then it is a tau function, KP tau function, if and only if the pi lambda satisfy the Plucker relations. And that's why there's a one-to-one corresponds between points in the Grassmannian and the tau function. So the left-hand side, what defines this coordinate ring is it's not a free ring, it's the relations, and the relations are these quadratic Plucker relations. Now that's the left-hand side. So what makes it a homomorphism is that the object that he wrote down as the image of the Plucker coordinates themselves also satisfy these same quadratic relations that the Plucker coordinates satisfy. But they're completely different objects. The pi lambdas are just complex numbers. And the h's are functions of an infinite number of parameters t, and they also depend on these auxiliary x's that define the lattice. So what does it mean that they satisfy the Plucker relations? Well, they are defined, as he defined rather quickly, they're defined by taking the tau function, whose Plucker coordinates are pi lambda, taking the tau function and evaluating it not at all continuous values, but at a lattice of values, okay? A lattice which is obtained by translations by these lattice generators, which there's one for each parameter xi. Now, those are evaluations of a given KP tau function, their functions. And the fact that they satisfy this really infinite set of quadratic relations, which are the image of the Plucker relations, is a highly non-trivial statement which comes from deep in the literature, and it has a name. So these functions satisfy the same quadratic relations as the Plucker coordinates, and the name of these relations, just to maybe make contact with something familiar, is the so-called addition theorems. The addition theorems are identities that are satisfied by KP tau functions, and in particular, they're satisfied by very well-known functions from the 19th century, like which were invented by Riemann, the Riemann theta functions. Riemann theta functions are sort of the examples par excellence of KP tau functions. And if anyone has heard of the Fay identities, these Riemann theta functions satisfy quadratic relations, which are the Fay identities, which come from the abelian nature of the group acting on the well, I won't go into the details, but of the abelian nature of the group. So that's a highly non-trivial statement. These addition theorems, which Semeon did not write down, are the basis for this proposition. And I would suggest, actually, if Semeon, if you have the addition theorems, it would be best to write them down so the audience can know why this proposition is true.
Let's first see if anyone has a question. I suggest that.
Well, I can add a quick question. I cannot resist. So let me know if you answered the question already in the talk, but can the solution be, restricted to the finite KP equation with only 3 variables, or?
Yes, that's kind of this infinite dimensional lattice. If you consider a sublattices, then everything will work. In particular, you can look at the 3-dimensional sublattice, right? Mm-hmm. And take only kind of lambdas which fit into the certain, n by n box, and then you will get and kind of oh, sorry, let's take n-dimensional sublattice and also take lambdas which fit into n by n box, and what you will get is a n-dimensional lattice of points in Grassmannian n to n. Same for Lagrangian Grassmannian n to n if you start with the CKP tau function, etc. It's same in the 3-dimensional case, where you get the famous mu recurrences.
I have to jump in here because I think William's question was one thing and Semeon's question was another thing. His answer was another thing. William was asking just about, we have this infinite set of equations, and he's just asking about the 3-dimensional problem, which is the 3-dimensional partial differential equation, which is the KP equation. Now, that reduction, that's just a subset of the equations. That has nothing to do with reducing from infinite to finite in Grassmannians. What it does have to do with is just picking out of an infinite set of equations one particular equation. However, what Semeon's answer provided, which had nothing really to do with William's question, was you can reduce from an infinite Grassmannian to a finite Grassmannian. That's finite in a completely different sense from what you meant. And doing that, reducing from, embedding everything or reducing to everything to a finite dimensional Grassmannian provides a particular class of solutions of all these equations, not just the KP equation itself, but all the equations of the hierarchy. And that class of solutions, which correspond to embedding finite dimensional Grassmannians and infinite dimensional, include in particular polynomial solutions, which we heard a lot about in other seminars, and also so-called solitons, which are ratios of linear combinations of exponentials. All of those fit into the finite dimensional reduction, but it has nothing to do with reducing to one particular equation in the hierarchy. It only has to do with the class of solutions that provides.
Oh. William, let me just say, so to get back the original kind of KP equation from that, you essentially look at the equation on U1 and U2 and exclude U2, where and you actually get the PDE on only T1, T2, T3, which if you change to X, Y, T, that's what you will get. What was this the question, or the question was about lattices?
No, the question was about recovering a solution to this particular equation.
Yeah, it's just one of the equation, kind of one of the functions here.
So it's rather trivial to specialize the general solution to the original KP equation.
Yes, yes.
Even though the original KP equation doesn't seem to have a natural solution when you only formulate it in terms of 3 variables. So it's kind of interesting in the end that.
Well, there's a, okay, if I could just help here a little bit, there's a natural grading in all of this, which is given by powers and by weights of partitions and so on. So when you write down this list, it's possible to write a list, a countable list of equations, which are the KP hierarchy. There's a natural way to order them. And the very first equation, but there's an infinite number of them. And some of them involve independent variables that are T1, T2, T3, or T6, T15, T19, or whatever. All of these equations involve 3 variables at a time, but there's an infinite number of them. And the very first non-trivial equation in the list is the one you were asking about. That just fits into a whole hierarchy. So the same tau function gives you solutions simultaneously to this whole infinite set of equations. Any solution, any tau function does that. And in particular, you just read off the first from the list.
Beautiful.
It sounds,
Sorry.
yeah.
So I was going to say, just to follow up on this final proposition, you mentioned I'm afraid I don't know who Jay's first name is, mentioned sort of the Fay trisecant identities. And, you know, when I sort of think of those, I think that I've got this Siegel space, which tells me about my Riemann matrices. And these identities are sort of cutting out a variety, which tells me which of these matrices really give me actual Riemann surfaces. And that would be how I sort of typically picture this, that, you know, we have some space of all possible tau functions, and the fact that they, you know, if they actually satisfy these Plucker relations, that tells me if it actually gives me a tau function of the KP hierarchy. So what is this proposition then telling me, you know, within that story?
Well, it's a slightly, I would say, it's a slightly different direction, because here we start with some tau function. We start with some tau function which correspond to the element of the Grassmannian. So you already pick a point in this kind of master Grassmannian, and then you evaluate this tau function on a lattice with appropriate normalization coefficient. And what turns out is that for every base point on the lattice, the neighboring evaluations are actually Plucker coordinates which satisfy Plucker relation, but not of the original kind of the original point in the Grassmannian W, but kind of they give you some different point in the Grassmannian. If you change the base point of the lattice to a different base point, then this the evaluation of H at the neighboring point would again give you a Plucker coordinates, but now of a different element of the Grassmannian. And these Plucker coordinates, they glue together in a nice way on a lattice. So what used to be, you know, one Plucker coordinates, if you think of N0 as a base point, can be another Plucker coordinate of another point if you use M0 as a base point. So that's what the statement is about.
I see. So this is your sort of relation to your comment about integral systems, that in a way this is generating other tau functions because we then have this lattice structure.
Yes.
So is there an analogous, or is it because we have the concept of function evaluations? Is this what makes this unique? So I can't do a similar thing when I am on this Augusta variety, when I pick out, you know, a point that's on the Augusta variety within the modular space that tells me that I get a Riemann surface, you know, is it absolutely absurd to think, or maybe fantastically, there's a lattice that sits in there that somehow gives me a way to find new Riemann matrices?
Well, in short, I don't know, but that's a valid question. Yeah, I just never thought in that direction. So yeah.
Maybe I could jump in. I'm not sure who's asking the question, but I presume that you're in algebraic geometry.
Integrable systems, algebraic geometry, somewhat, yes.
All right. Well, I think okay. If you know about integrable systems, you know that the solution of the Schottky problem, in a sense, is given by KP. So if you take a theta function, just any old theta function, and you ask, well, which one comes from a Riemann surface? Then, as you probably know, Mulase and Sciotta proved that it is exactly those which come from the KP hierarchy. So if it is a KP tau function, then it does come from a Riemann surface. So in that sense, I don't know. I mean, I only know the Fay identities for theta functions associated with Riemann surfaces. Are there also such identities for theta functions which are not?
Yeah, I wouldn't know any immediately, but perhaps they exist.
Okay, so that's consistent with it's a bit of a long shot. I only mentioned the theta functions because I thought that might make contact with something familiar. So as far as I know, the Fay identities, and there are many Fay identities, the trisecant one is one version, but I'm thinking of the Fay identities which are quadratic relations satisfied by the evaluation of Riemann theta functions at different points. And yes, these quadratic relations indeed can be thought of as defining an embedding in a projected variety. And we do see that in this case also, even though there's not necessarily any Riemann surface or any algebraic curve, still these KP tau functions share a lot of the properties of Riemann theta functions, which are special cases. By the way, the same thing is true of Schur functions. I mean, theta functions are sort of the generic type of tau functions, but Schur functions are all KP tau functions as well. They're the building blocks, and they all satisfy these quadratic identities as well. So the addition theorems are much more general than just the Fay identities, but that's a very famous special case of them. I mean, you didn't see the addition theorem. The basis of this homomorphism is the addition theorem. So that's why I suggested to Semeon to display. It's not very difficult to write these addition theorems. In fact, there's a beautiful way to write a generating case in which there are just 4 parameters. Semeon, would you not like to write down the?
No, let me put it.
Write down the one with 4 parameters or 3 parameters.
No, let me actually do the one which is literally the statement used in the Plucker relations for. Okay, so
well, that might be a little overwhelming. If you have an infinite number of parameters, it might be a bit overwhelming.
I disagree.
So
you have a finite, but kind of. So let's look at the following thing. Let's define zeta n, and it will be a function of t and n parameters, not infinitely many, but n parameters. And it will be a particular case of what I wrote, but when we shift, by 1 in each direction. So that will be a product I less than j, xi minus xj, tau of t plus sum these parameters xi. I runs from 1 through n. And then the addition theorem for that would work as follows. So you basically take any parameters, x1 all the way through xk minus 1, and y1 all the way through yk plus 1. Probably you need some generous. Oh, no, you don't if this is a numerator. And then you look at the following sum, which almost looks as a Plucker relation. So that's, and in fact, it turns into a Plucker relations on these evaluations. Zeta k, and you essentially take this axis all the way k-1 and add 1 yj, right? And
so just to, I don't know what your first name is, Lyndon, just to make clear the correspondence with theta function. The
yj.
t over
Limited.
here. Can you hear what I'm saying? While he's
Yeah.
writing that, I just want
Here we
to
go.
make clear the correspondence with the theta function. The t should be thought of here as a linear coordinate in the Jacobi variety.
That's addition. Well, addition theorem or formula. And as you can see, it has the structure of Plucker relations, Plucker relation already. What is interesting is that if you introduce this quadratic factor in the evaluation, that kind of the same evaluation will be Plucker coordinate for different points in the Lagrangian Grassmannian corresponding to the different base points.
Okay, thank you very much, Semeon. Do we have any other questions? Any final questions or comments? If not, then let's thank Semeon again for a very nice talk. And thank you for this very interactive talk as well. That was much appreciated.
Thank you for the invitation.